Stefan's constant. Write the Planck distribution law in terms of frequency rather than wavelength to obtain I as a function of frequency. Part B, show that the integral from 0 to infinity I of lambda d lambda is given by this, where I of lambda is the Planck distribution. And there's a hint, change the integration variable from lambda to f, and you will need to use a tabulated integral. And part C, the result of part B is I and has the form of Stefan-Boltzmann law, I is equal to sigma times t to the fourth power. Evaluate the constants to find Stefan's constant, sigma. Okay. So let's start with part A. In part A, we're going to write Planck distribution law, which is given in terms of wavelength as 2 pi hc square divided by lambda to the fifth power e to the hc over lambda kt minus 1. Okay, and the speed of light c is related to the wavelength and frequency, lambda times the frequency, or for wavelength we can substitute the speed of light in vacuum divided by the frequency f. So if we do this substitution, we will obtain intensity as a function of frequency, which is 2 pi hc square. Lambda to the fifth power will become c divided by f to the fifth power. And then we have e to the hc over lambda is hf divided by kt minus 1. So if we take frequency to the fifth power upstairs and also take care of this c square and c to the fifth power at the bottom, we will obtain our final answer for part A. Intensity as a function of frequency, Planck distribution law written in terms of frequency rather than wavelength, is 2 pi h frequency to the fifth power. Now we have c to the fifth power, c to power 2, so they will cancel and we will be left with c cube at the bottom. And then we will have e to hf over kt minus 1. So this will be the answer to part A of the problem. Part B, we're asked to evaluate this integral from 0 to infinity I of lambda d lambda. Okay, so the integral from 0 to infinity, the Planck distribution in terms of wavelength I of lambda d lambda. This is actually, if we substitute frequency is equal to c over lambda here, you can see that when the wavelength is 0, we will have infinite frequency. When it's infinite, we will have 0 frequency. So this will become an integral from infinity to 0 instead of 0 to infinity. Intensity distribution as a function of frequency. And for d lambda, if you look at df, you will see this is minus c over lambda square d lambda. So for d lambda, we can substitute minus 1 over c lambda square df. And lambda is c over f, so we will substitute that here. So this will be minus 1 over c, c square over f square df. And you can see that we have one of the c's disappearing. So this gives us minus c over f square df. So this will become I of f minus c over f square df. And if I introduce the minus sign here, so you can see I have this minus sign, I can change the order of the integration limits. So this will become integral 0 to infinity. So that takes care of this minus sign. Now I have Planck's distribution law written in terms of frequency 2 pi h f to the 5th power 2 pi h f to the 5th power, but there's an f square here, so this will become f cube, 2 pi h f cube. Now I also have a c cube at the bottom and c on top, so that will become c square e to the hf over kt minus 1 df. So now this integral has been reformulated in terms of frequency rather than wavelength. So let x is equal to hf over Boltzmann constant times absolute temperature. So if we do this substitution, df will become kT thermal energy divided by Planck's constant times dx. So the integral, so you can see that when f is equal to 0, x is equal to 0, f is equal to infinity, x is equal to infinity. So the integration limits don't change, 0 to infinity. Now for df, I substitute kt over h dx, and I have a c square here, so this will be kt over c square h, and in Planck distribution I have 2 pi h f to the 3, so that's f cube. Then I have e to the x minus 1 dx, and I can see that one of the h's, so these h's will disappear here. So I will be left with 2 pi kt over c square, 2 pi kt over c square. The integral from 0 to infinity f cube dx divided by e to the x minus 1. Now the question is, what is f cube? F cube is thermal energy kT divided by Planck's constant cube x cube. So when I substitute that here into this integral, this will be 2 pi kt over c square remains, 2 pi kt over c square. For f cube, I'm substituting kt cube divided by h cube, and this is the integral from 0 to infinity x cube dx divided by e to the x minus 1. Okay, so if I clean this up a little bit, so that I have kt cube and kt, this will become kt to the 4th power. So I have 2 pi kt to 4th power divided by c square h cube. So that's the bottom. And then I have the integral from 0 to infinity x cubed divided by e to the x minus 1 dx. And this integral was given to me, integral 0 to infinity x cubed over e to the alpha x minus 1 dx. Now alpha is 1 here, so this is 1 over 240, 2 pi to the power 4. So this is going to become 2 pi kt to the 4th power c square h cube. The integral is 1 over 240, 2 pi to the 4th power, so I note that alpha here is 1 for the given integral from the table of integrals. So this gives me, because I have now 2 pi and 2 pi to the 4th power, 2 pi to the 5th power. So this will be 2 pi to the 5th power, kt to the 4th power, divided by 240 h cube c square. So this is, now if I consider 2 to the 5th power and 240, this will give me a simplification for the 240 here. So I will have 2 pi to the 5th power. So top and bottom divided by 16. Kt to the 4th power. 240 divided by 16 gives me 15 h cube c square. So basically, I have shown that this integral gives me 2 pi to the 5th power, k to the 4th power, t to the 4th power, divided by 15 c square h cubed. That's exactly what I have found here. So this has been shown. Okay, let's move on to part C. Now, part C says the result of this integral is intensity is I, basically, so that has the form of Stefan-Boltzmann law, sigma to the 4th power. The intensity is average power per area, remember, and if this is done for a black body, emissivity is equal to 1, so this is equal to sigma times t to the 4th power. So the Stefan constant in that case, we can observe, is equal to 2 pi to the 5th power, Boltzmann constant to the 4th power, divided by 15 h cube c square. Now, if we plug in the numbers here, this will become 2 pi to the 5th power, Boltzmann constant 1.38 10 to minus 23 joules per Kelvin to the 4th power, 15 times 6.63 10 to minus 34 joule seconds, Planck's constant. Speed of light in vacuum is 3 times 10 to the 8 meters per second square. So this gives us, for the Boltzmann constant, Stefan-Boltzmann constant, 5.65 times 10 to the minus 8 watts per meter square Kelvin to the 4th power. So we have evaluated Stefan's constant and we have found that it's given by the number that we are familiar with. Okay, so what have we done here? First, we write the Planck distribution law in terms of frequency rather than wavelengths. The Planck distribution law is given to us. So in order to go to frequency, we use the relationship C is equal to lambda F. So for lambda, we substitute C over F. Doing so, we obtain this intensity as a function of frequency. In part B, we take the integral from 0 to infinity, integrate the Planck distribution over all wavelengths and find that it's given by this expression, a constant times absolute temperature to the fourth power. And in order to prove this result, we use intensity as a function of frequency. So F is equal to C over lambda. We do this substitution, and then we use X is equal to HF over KT substitution. And these two substitutions basically give us an integral from 0 to infinity x cubed dx over e to the x minus 1, which is given as x cubed divided by e to the alpha x minus 1 dx, integral from 0 to infinity. 1 over 240, 2 pi over alpha to the fourth power, but here alpha is 1, so it becomes 2 pi to the fourth power. So by substituting this, we obtain this result. And here we recognize t to the fourth power is has a prefactor which is a constant, and when we evaluate that constant, we obtain Stefan's constant.